right, I think we'll start in about a minute or so. All right. Go ahead and start here. I've got the chat open. The chat's delayed by like 15 or 20 seconds. So if you type something and don't answer it right away, then I might not have seen it, or it might just not have come through yet. So this is statics and mechanics of materials. We got the Moodle page open here so you can look at that. You should have access to this one. There are two Moodle pages. Some of you are in a section V84 and some are in a section 084. I'm using the V84 Moodle page, so everyone should be in that one. If you don't have access to that one, then let me know so I can put you in the V84 section so that you can see all the stuff. The other section is basically empty as far as the Moodle content goes. So I've got kind of the layout here. This course is a sophomore level engineering course, so it's statics and mechanics of materials combined together. So unless you're civil engineering or mechanical engineering, it's possibly the only course that you'll get that talks about statics and mechanics of materials. Sometimes these are two separate courses, an individual statics course and an individual mechanics course. But we combine them together. We have a book. Let's see, I have a picture of the book. There it is. We're using this book. I don't reference it directly a lot of times. Our homework is handled through WebWork, so you'll have homework online outside of there. The book, though, does give you some reference material, gives you more like written explanation about things, and more problems to practice on. So we will use that, but I don't reference it too often here. I grabbed some, in fact, this folder right here with reference materials is filled with material that we'll get from the book. We've got 3 exams, so they're cumulative in the sense that they kind of do build on one another, but it's not necessarily that exam 1 is or exam 2 is dependent on exam 1. I guess it's not necessarily that way. But there are concepts that move from one to the other. The general thing, though, is that the first third of the course, up until exam 1, is axial. So forces that are pulling or pushing on an object. And then the middle part, the second third, is more bending. So the forces are making something flex or bend. And then the last third are a couple of random topics that don't really fit well into the others, and twisting. So forces like torques are creating twisting motion on these objects. And so the idea of statics is that we're looking how these forces are applied, how they balance each other out, and we're looking more at the forces themselves and how they are how they exist in this object or this collection of objects or whatever. And then statics, well, no, that's statics. Mechanics is more about what those forces do to the actual parts they're applied to. So do they stretch them? Do they stretch them so much that they break? Do they crush things? Stuff about how the material itself responds to whatever force is applied to it. And this course does not go and combine all of that together. So it doesn't have a problem at the end where it's being pulled and flexed and twisted all at the same time. So that's a little bit higher level course. If you're mechanical or civil engineer, you'll probably take one of those courses. If you're not one of those majors, you'll probably not get into that combined loading unless you take an elective course that would tell you about that. So the layout here is we start with stuff that probably you've seen already, hopefully you've seen already. So I'll go through it kind of quickly, just with 2D concurrent forces. So at the end of the day, there shouldn't be anything that is completely new. There might be like little nuances or something that are new, but the topics themselves shouldn't be brand new to you. If they are, like if we go over something today that you've never seen before and you don't have any clue how to do it, then definitely reach out for some assistance on that, because the stuff we're doing today, we kind of assume that you've got a decent handle on. Maybe you've not mastered it yet, but you have seen it before and maybe dealt with it a little bit. And then from today on, after today, then those will be pretty much new topics. You might have seen little bits and pieces of them before, but they'll mostly be new stuff. But today should be things that are kind of background, but we're going to go over them just to make sure that we're kind of all on the same page starting wise. Let's see. Let's look at the syllabus, or well, the grading thing here, so that we can, I guess this whole thing is the syllabus. There are several different assignments that you're going to complete. Maybe we can make that a little bigger. There's a design project at the end. Now I know most of, or well, I don't know how many, but some of you aren't even in town. So you're off doing an internship or whatever, and there are ways that we can still complete this design project without you being here in person to do stuff. But that's a 10%. It's towards the last third of the quarter, so we don't need to worry about it too much yet. There's the web work, homework. That's another 10%. If you haven't already been able to log into web work, then you will be able to soon, and that's where our homework will appear. Basically, we'll do a lecture, and then you'll have a web work assignment that will be due about a week later, a week after we talk about it. There's some lab assignments. These are, if we were on campus, we would go physically do these labs. Like we would go to a machine and break something. Since a lot of us are not on campus, then these are going to be SolidWorks simulations. So you should have access to SolidWorks or something like SolidWorks. And I'm going to show the examples in SolidWorks. And we're going to run some simulations that would model what's going to happen in our lab assignments here. There are 5, I believe, Moodle quizzes, each worth 2% of your final grade. These are online. They're in Moodle. They're set up to be more of the more direct type of questions. So there might be 5 questions on there that are 1-step, maybe 2-step type of problems. Things that should be not easy, but straightforward to solve. And they're kind of a gauge for if you're doing the quizzes and you're making 90s and 100s and whatever, then you're probably good with the foundational stuff for the exam. The exams will have harder questions from time to time. They'll also have questions like what are on the quizzes, and they're kind of just a gauge to make sure you're on track. There are 3 exams. I've got E1 and E2. That's exam. Oh, I'm missing a parenthesis there. E1 and E2 are exam 1 and exam 2. So whichever of those you do worse on, so the lower exam, it will end up counting 15% of your grade. Whichever one you do better on will count 25% of your final grade. The final exam, it's a separate exam. It counts 25% no matter what. And it is cumulative in the sense that it will contain questions that go all the way back, possibly to today even, and through the new material. There's not as much new material in the last third of the quarter as there are in the first and second thirds. So this grading scale is in Moodle here. You can look at it if you want to reference it again. I guess I probably should have checked to make sure those added to 100%. I assume they did. If they don't, then I'll fix them. I'll go back and check that. Like I said, this is the textbook that we'll use for reference charts, things like that. Here are some scans of materials that we'll also use. And I think that's probably, I don't see any questions in the chat, so everything must make sense as far as that goes. Let's go and get into, well, let me, before we get into that, there is a Discord. You should have gotten an email, and I think if you scroll down further here, there's some links to a Discord channel that you can ask questions on. There's a sign up a digital sign-up thing if you need office hours. I don't have a lot of office hours during the summer, so that's probably pretty limited. But and there's an email address, so you can send email, you can ask questions in Discord, or you can set up like a Zoom meeting if you need like that kind of help on any of these topics. I will be on campus some on Tuesdays, so that would be the day that if you needed to see me, that'd be the best day for that sort of thing. All right, let's go over here to well, let's get that out of the way. Let's go to here, and we'll work over here. This is just one note, so I can write stuff on the screen so that you can see what I'm writing. All right, so the idea for today is, again, today we're all statics. So we're not really talking about mechanics today. So this is more intro things, and it's all the statics. So how are the forces acting, and what are they doing, stuff like that. What are forces, that kind of stuff. So let's start. Let me look at my notes over here. Let's start with, well, how do you even define a force? So that's a good place to start if we're talking about forces. So let's figure out how we can define a force. So you've got the idea probably that you can define a force. It needs a magnitude. So it needs some kind of number that tells you it's 10 pounds or 30 newtons, something like that. We do have both systems in this course, so we will have to translate between pounds and newtons and meters and inches and things like that. So you do have to have a way that you can translate between those two unit systems. Some of the test questions will even have mixed units in them to make sure that you can translate between the two. Some of the problems and homework will have mixed unit systems, just to make sure that you know how to get from inches to centimeters and such as that. So we need a magnitude for our force. We also need a direction. So we are going to usually use some sort of, make that a little bigger. We're usually going to use some sort of angle. It may not be always an angle in degrees. You know, there might be radians, or there might be a rise and a run, and you figure out the angle from that. So it won't always necessarily just be a force at so many degrees above horizontal or whatever, but there will be something that indicates the direction that this force is going. And then the last thing you need, those two things by themselves do define like a force vector, but here this force vector is applied to an object. So this object experiences this force, and so we need a point of application. So this force is going to be pulling on the rope, or it's going to be pushing on this block or whatever. And so we need to know where it's pulling and where it's pushing and that sort of thing. So if we have those three things, then we'll be able to do the next thing that we would want to do. So let's kind of draw out what that might look like in a very abstract kind of way anyway. Nothing too particular here. I typically try to use colors to show different things on the diagram. So green is usually some kind of coordinate system. Blue is some kind of dimension usually. Red is usually a force. And then any kind of black line like I've got the text in is either a piece of text information, or maybe it's the object itself, like its boundary, something like that. I don't know if I'll get that exactly the same every time, but that's typically what I do. So here we're just drawing, again, we're doing 2D today. So we're just drawing a 2D coordinate system. So this is our x-axis and this is our y-axis. And we want to put a force inside here. Now, right now, we're not worried that this force is doing anything in particular. We just need to be able to manipulate some things with the force for now. And it'll do something in a few minutes. So Let's just put a four. Well, I wanted to make it an actual arrow. There we go. Let's make it like that. So here's our force arrow. This one needs some sort of angle. So we'll say that our angle here is, I don't know, that looks like 30 degrees from the x-axis. It needs a magnitude. So let's say that it is 40 newtons. And it has a point of application right here at the origin of our coordinate system. The point of application will not always be at the origin of our coordinate system, but when we have these things called concurrent force systems, that means a particular thing, and usually the point of application of these force vectors is at that origin. Why don't we talk about concurrent forces for a second? Actually, we need to talk about one thing before we talk about concurrent forces. Let me move this over here so that we can do it. So this force vector that I've drawn, it has what's called a line of action. So its line of action would be like if I took and extended it pretty much indefinitely in both directions. That is what we're calling a line of action. So that line of action is going to be useful when we start defining our idea of a concurrent force system. Looks like I didn't quite draw them straight. That's okay. Let's scroll down some here, or make that go up, and let's talk about this concurrent force system. Today we're talking about 2D concurrent force systems. Next time we'll talk about 3D concurrent force systems. They both are concurrent force systems, and they both follow the same rules, just one of them is in 3 dimensions, x, y, and z, and today we're just in 2 dimensions, x and y. So what concurrent force system means is that all these lines of action, no matter how many forces I have, I could have, well, I need more than one for it to be a system. So I need 2 forces or more, and they all have one thing in common. So all lines of action intersect at a common point. So no matter how many forces I have in the system, all their lines of actions will intersect at one point. So that might look like some of these things. Let's do a couple of examples of what this might look like. So I'm not going to draw the coordinate system right now. I'm just going to draw the vectors. So there's a vector, and let's put another one out there right here. And so they both have lines of action. Here's one. That first vector I saw that drew, there's its line of action. Second vector, its line of action. And then here's that intersection point. That intersection point, all the lines of, I only have 2 forces, but all the lines of action, all 2 of them, intersect, and that point is concurrent with all these forces. They share it in common. That's also a good point to put the origin of a, if I'm drawing the XY coordinate system, that point is a good place to put the origin of that coordinate system. Let's draw one that's not concurrent. So this is a new force system from the other one. Here's vector 1. 2 of them, they'll always intersect, right? You'll always have them where they have some point that intersects. But if I add a third one, I don't always get that one intersection point. So if I added this force, then okay, yeah, that still intersects at that same point. So I've still got a concurrent force system. But if I add one that, over here, this one's line of action it's intersecting in some totally different places, like over here and over here, and this one not concurrent. Now we can deal with that later, but for today we're going, and actually for the first couple of days in our course, everything's going to be concurrent. Actually, maybe, well, not everything for the entire first third of the quarter, but a lot of the stuff in the first third is concurrent. Not everything. There's a couple of things that aren't, and we'll get to those in a couple of days. So this one, we created these new, this point, and now we've got a third point. So there's 3 points where they intersect. Not a concurrent force system when I added that third. Oh no, that was the fourth one, wasn't it? When I added that fourth vector, that one made it not concurrent. The third one was fine. It still had everything intersecting back over here at that original intersection point. But when I added that fourth one, it did not intersect that same point. And so that system would not be concurrent. So we have to deal with that one a different way. Usually what we're wanting to do here when we have a force system and we're talking about some kind of statics is the word static means something in this course. And it means what static normally means, like not moving, not changing, stationary, something like that. And that's what static means in this course, is that we aren't moving. At least we're in equilibrium. We're in static equilibrium. So we could be moving, possibly, like maybe rotating, and it looks like we're moving, but we're not translating anywhere. So we're not like moving in the X direction or the Y direction. But we are in what's called static equilibrium. And so that's important. That equilibrium part means that, well, look at the word, it's equal. So there's something there that's equal. And we've reached this state where things have balanced out. It doesn't mean that there are no forces. There's always going to be some kind of forces, unless we're weightless in a vacuum somewhere. Then even then we could introduce some forces, but there's always going to be some kind of body weight, electromagnetic force, a wind force. There's always going to be something, but sometimes we apply forces, like we push on things. So static equilibrium means that we're pushing on stuff, but it's pushing back, or there's other things that are pushing back at us, and it's all balanced. So if we remember, I think it's Newton's second law, right? Newton's second law. Newton's first law is the one that's basically objects at rest tend to stay at rest, and if they're in motion, they tend to stay in motion unless you act on them with an outside force. So that's the first law. The third law basically describes the idea that for every force, there's an equal and opposite reaction. That's going to be important. Actually, all of these laws are going to be important in this course. But the second one is the one that gets described with an equation, that force equals mass times acceleration is Newton's second law. But when we're in static equilibrium, then the acceleration is 0. So we're not accelerating. So in static equilibrium, I'm just going to abbreviate there instead of writing the whole thing. Acceleration equals 0. So if I take that idea, acceleration equals 0, put it into Newton's second law, it says F equals mass times 0. That also says that, well, mass times 0, anything times 0 is 0. So it says, this is my little, these little 3 dots in a triangle. That's the word therefore. So if F equals mass times 0, therefore F equals 0. So that's weird, because we know we can push on things and apply a force, or it has a body force, it weighs something. So we know there's forces there. So it doesn't actually mean that force equals 0. What it really means is the summation of forces equals 0. I'm going to use the capital sigma there for summation. Summation of forces equals 0. And what we're going to do with that is that it's not really just that all the forces add to 0. I've got a 10-pound force going left, and I've got a 10-pound force going up, and they cancel out somehow, or I've got a -5 and another -5. It's not that they add to 0. It's I have to add them in certain directions. So here's where we have a choice to make. We could take this course and remember we started with these vectors. So we could do vector math to keep track of directions and the directions and magnitudes of these vectors through IJK coordinates and all that kind of stuff. We could do the vector approach to adding these forces together. We are going to, in this course, pretty much exclusively, I can't think of when we wouldn't do this, we're going to use rectangular coordinates. So the x coordinate, or not coordinate, components. The x component of this force, this 40 Newton force, or the y component, or the z component. So we're going to do x, y, and z components of forces. And our little summation of forces equals 0 equation is going to expand into the summation of forces in the x direction equals 0. The summation of forces in the y direction equals 0. And the summation of forces in the z direction equals 0. There's one other also that we'll deal with later because things can rotate. But we're in a concurrent force system, things aren't rotating. So we don't have to worry with that one yet. We'll do that in maybe 2 weeks. So what this tells me is that I've got 3 different directions, x, y, and z, but today we're in 2D concurrent forces, so I only have x and y. I don't have the z direction today. So x and y forces have to add to 0. So what that means is that for every amount of force that I push in the x direction to the right, I'm assuming x is horizontal, then I have to push an equal amount in the x direction to the left. And same thing with up and down in the y direction. And so what that means is that I need to be able to figure out, like in this force, what is the amount of this 40 Newton force that's pushing in the x direction, and what amount of it is pushing in the y direction. It's not 40. It's only a piece of that 40. So we need to be able to do force components. So why don't we just take this one? In fact, it's already drawn. Let's just take this one and copy it. Oops. And we'll put a new version of it down here. Okay. Let's do red and the x component of this guy. So I want to know, what is that guy? That one is the x component of the 40, I did Newton force. So if you're careful in drawing these things, like if that really is 30 degrees, I guess I could find a protractor. Let's see. This is actually 25 degrees. So if I measure it with a protractor. So if I actually drew these out accurately, and that length of the 40 Newton force was proportional to whatever this x component is, then I could actually use the picture itself, the diagram, to tell me that I know one thing. I know this x component is less than 40 newtons, but I could actually measure their lengths if I had drawn everything accurately, and I would be able to kind of get close to the value of this x component just by measuring it. I'm not going to say that that's how we're going to solve things in this course, because that would be a little bit tedious and not as accurate as we can be, and it's not really hard to solve this anyway. But if you are more accurate, you know, either really good at estimating angles or in these lengths of vectors, or you use a ruler and a protractor, then your diagrams will give you more information than just a picture. They'll actually give you like relative sizes of forces and directions and things like that. I'll try to be relatively accurate when I draw these, but I'm not going to worry about it too much. Let's draw the y component. So the y component, I'm going to draw it on the y-axis, but I'm going to draw it twice actually. So it's over here. So that one is the y component of the 40 Newton force. Notice that vector is way shorter than the x component, like half of it. Just by assuming that our 30 degrees is more or less right, drawn correctly, then we could kind of tell that, well, the y component is about half of the x component as far as magnitude goes, and the x component is maybe like, I don't know, 80-something% of the 40 newtons. We want more accurate than that. We don't want to just guess at these things. So we're going to use equations. We're going to use trigonometric equations. We're going to mainly be using sine, cosine, and tangent in here. And mainly sine and cosine. We don't have to use tangent too often. So let's write down the definition of those. So sine of an angle, I'm just use theta here. Sine of an angle is the opposite side over the hypotenuse. That's the definition. Cosine is the adjacent side over the hypotenuse. And if we use it, tangent is the opposite side over the adjacent side. So their lengths or their forces, their magnitudes, whatever, those actual numbers can be used to calculate these angles, or the inverse sines and cosines and tangents can be used to calculate one of the missing pieces of information here, the hypotenuse or the opposite side or adjacent side, whatever we're looking for. Let's move this. I've selected the y component that I drew on the y-axis. I'm going to copy it and paste it and put it right over here. We'll erase that little s. We don't need that part. So when I did that, we created a little right triangle. And that triangle is what we will use these sine and cosines on. So if I want to figure out the x component of the 40 Newton force, for instance, then I would go in and the x component, if I'm thinking of this 30-degree angle here, the x component is the adjacent one to the 30 degrees, and the 40 newtons is the hypotenuse. So the adjacent has to do with the cosine. So I could write cosine of theta equals the adjacent side's length or magnitude, either one, over the hypotenuse of the triangle, in this case the 40 newtons. So filling in the things that I know from my picture, cosine of 30 degrees is equal to the x component. Let's write that one a particular way. Let's write it fx. So the x component of the force, and the force is 40 newtons. And then the hypotenuse is f, the 40 newtons. So therefore, I can solve that equation for fx, the x component of the force. So fx is equal to cosine 30 degrees times 40 newtons. I've got MathCAD running over here so that we can, somewhere over here, there it is, we can write these things down. So what was it? Fx is equal to the cosine of, I'm just going to hard code these in. I'm not going to use variables or anything today, or at least not right now. So that was 30 degrees. If I don't put the degrees in MathCAD, it's going to think I'm talking about radians, so I'm writing 30 degrees. Cosine of 30 degrees times 40 newtons. And that equals 34.641 newtons. So 34, and okay, this is a good point to make about how many of these decimals do we need to deal with. It doesn't really matter, except that we're not going to track scientific, notation. We're not going to track number of significant variables. We're not going to track that kind of thing, or significant digits, I meant. We're not going to necessarily go and try to figure out, this one looks like it probably has maybe two, at least one significant digit, but we're going to, we're going to just do what's reasonable. We're going to do what's reasonable on the number of digits that we're going to use. So 34.6 is probably reasonable. It really gets down to, in engineering, first of all, what can you measure? Can I measure with whatever my tools are in this scenario? What can I measure 34.641 newtons? Because if I can't measure it, then why do I put it down here? Or what can I cut? What tolerance can I hold if I'm talking about a dimension? What tolerance can I hold reasonably to manufacture that thing? In this case, I'm talking about forces, but sometimes there'll be dimensions. So a lot of times it comes down to what's reasonable. Now, when you're doing your homework, web work is, it does not like to round much at all. I think there's maybe like 1% rounding tolerance in there, but it doesn't like to round at all. So in web work, you're probably going to want to use a lot of decimal places. In real life, you go down to what's reasonable to either cut or measure, or what can you actually deal with. So I would call this 34.6 newtons and be fine. The exams are set up in a way where most of the time you're answering a multiple choice question, so you don't really have to decide at all. It's just one of the choices. But that's just typically I don't want to see you solve a problem like this and then go, where's it at? Go out here and run out the decimal places, something like that. That's, your calculator may tell you that, but that's a little bit not real. So use 2 or 3 decimal places and you're probably fine for most things, unless it's a really tiny number that needs a bunch of decimal places. All right, so 34.6. Let me get back to our page over here. So if we were looking at this, Fx equals 34.6 newtons. Now, based on our picture, we've looked at it, and it looks like our y component is about half of that. So when we solve for our y component, we're expecting around 17 newtons or something. So that's one good thing about drawing your diagrams relatively accurately, is that you can get visual information that helps you confirm or look for mistakes in your calculations. So let's calculate our y component and see if we get somewhere around 17 newtons. So we would do the same exact thing, except now instead of a cosine, we would use sine of theta is equal to the opposite side